Well, hello everybody. So here's a problem I found on our assignment on my math lab, and I think it's a good problem to do, so here it is. So I'm given this two-dimensional region that's contained or bounded by these curves. X is equal to 2y and x is equal to y squared minus 15. And if I look through the parts of this question, it asked me to solve for that area or calculate that area in two different ways. Okay. So the first part of the question says, what's the area of the region in terms of x? And what it's looking for here is, what's the setup? How would you set up a definite integral to measure or calculate that area right there as you see it? So let me go through the steps for that. Here's what I think we'll need to do. First, I noticed that as this region that's shaded right there defines an area that I'd like to calculate, it's contained by certain things. It's contained by this parabola and this line, and then they meet each other or intersect at 2 points. So you're going to need to know those points of intersection. So look at it like this. I've got that curve, x is y squared minus 15, and the line, x is 2y. I just need to find some common point on both of those. So that means I can solve them as a system. If they're both equal to x, then they're both equal to each other. And I get this equation. And then that's the kind of thing I can solve by either factoring or the quadratic formula. I solved it by factoring. And I get two solutions. Y is either 5 or negative 3. Now I'm solving for points of intersection. Points have an x and y coordinate. I've solved for the y coordinates initially. So to find the x coordinates that go with the y's, take y is 5 and put it in either one of these. Either way, you're going to get x is 10. Why do you get the same answer either way? Well, because these are points of intersection. These are points on both of those things at the same time. Same thing with y is negative 3. What's the x coordinate that goes with that? Take y being negative 3 and put it into either one of these, and then you'll get negative 6 either way. Okay, so there are my 2 points of intersection. Now, when it says what's the area of the region in terms of x, here's the model that we're going to use. So think of it like this. There is some region that you're trying to find the area of. So I've shaded that right here. There's a curve f of x which bounds that region from above, and another curve g of x which bounds it from below. So f of x is above g of x, okay? Or you could say f of x is greater than g of x. Now that's from a on the x-axis, which is here, over to b on the x-axis. B is greater than a. If you've got that scenario, f of x on top of g of x from a to b, then you can calculate that area like this. It's the definite integral from a to b, f of x, curve on top, minus g of x, curve on the bottom. Okay, so that's the model that we'll be using to solve for the area in terms of x. Okay, it's not the only way to do it, but that's what it's asking us to do. So I think to do that, notice how I say here, these are functions of x. What's a function of x? It's going to look like y equals, and then you'll have some formula that has x in it. And that's not the way these curves are given. I mean, that's backwards from what I would need. These aren't functions of x. These are functions of y. To get functions of x, I need to solve them in terms of y. And the one I think might be a little tricky is this parabola. So let's look at that. So the parabola, as I'm given it, is a function of y. X equals y squared minus 15. You plug y in, you get x out. That's what I mean when I say this is originally given as a function of y. I want to solve for it in terms of x, okay? Giving me a function of x. Now, when I solve this for y, and getting it in terms of x, notice I'd have to move the 15 over, it'd be plus 15, and then I have to take both the plus and minus root of the other side. When you solve for a square, you take plus and minus root of the other side. So what that does is it divides it into two different curves, two different equations. When you have the positive root, you get this one on top there, which I've outlined in red. So this portion of the curve, the upper curve, is y equals positive root x plus 15. That'll get you this upper half and the upper half only. Solving for the negative root, which you see here in green, outlined in green, you get y equals negative root. That should be x plus 15. Oh, that's going to bother me. That shouldn't be minus, it should be plus. Okay, so there we go. That's minus root x plus 15. Okay, so there I can't solve for that entire curve as one function of x, but I could divide it into two parts. I can say this part, this is one curve, y is root x plus 15, and then this other one, if you needed that one, would be y equals minus root x plus 15. Okay, so that's what I see as step 2 is if I'm going to use this model, the equations for each curve that's involved in this needs to be a function of x. The variable's x in this integral. Okay, all right, now let's do this. We'll divide that picture, the one we started with, into two regions, and we'll set up the integrals. So here I've redrawn it and I've divided it up. Okay, I don't see that this model applies to the whole picture the way that it is. It's not true that in this picture that there is entirely one curve on top of or above another one throughout the whole region that I'm looking at the area. But if I divide it into parts, it is. So see, like this part right here, I'm going to go right up to that point of intersection, which I found to be -6 and -3. Okay. Right up to that point, you have the upper portion of the parabola, which is y equals root x plus 15, above the lower portion, which is y equals negative root x plus 15. We solve for those over here. So at least from -15, this vertex, over to -6, this is on top of that. So that's region 8. That's what you see in red. And so I can use this model to set up a definite integral to find its area. I take root x plus 15, take away negative root x plus 15, and that goes from along the x-axis from -15 over to 6, -6. Okay, so there, that'll tell me this much of it. Now about that other part over there, the part that's in green, so that's different. In this part, I see this parabola is exclusively above the line. So in the green region, which takes you the rest of the way, parabola given by equation root x plus 15 above line. So how'd they give me the line? X equals 2y. That's easy to solve and get as a function of x. Y is x over 2. Okay, so I'll get that minus x over 2, and then that goes from x is -6 to 10. All right, so well, that's this part. So there they both are. Neither one of these individually will give you the whole region, but together they do. So I solve each of these definite integrals using the fundamental theorem of calculus. I'd have to find the antiderivative and so on, and I get 36 for one, 148 over 3 for the other. Step 4, the total area. Add those together, I get 256 over 3, which is the right answer. Okay, so that's integrating or solving it in terms of x. Okay, it's important to know that the model looks like this, and even if the model doesn't apply altogether, then I can divide it into parts and it will. All right, so let's look at the next part. So next part turns the question around and it says, what's the area of the region in terms of y? So the model is different this time, and I guess you could restate the question like this. It's asking us, can we use this model? So say I've got some region that I want to find the area of, and it's described like this. I've got some curve on the right, which is a function of y, and some curve on the left, which is another function of y, from some number a to b along the y-axis. So f of y is bigger than g of y, and b is bigger than a. Okay? If you can see that your region is described that way, then this integral will measure the area. Now, I think this one's easier because as this picture is, this line is entirely to the right of this parabola throughout the whole region. So look, I could say the line on the right, parabola on the left, and that would go from -3 on the y-axis up to 5 on the y-axis. Okay, now these would be functions of y in this case, meaning their equations would be in terms of y. They would be some formulas with y in them, but that is exactly how they were given in the beginning. X is 2y, the line on the right, x is y squared minus 15, the parabola on the left. So I don't really have to do any reframing of the problem in order to get this to work. Okay, I only need one integral in this case. I don't have to divide it into parts to get the model to apply. All right, so there's that integral that I just described. I got the curve on the right is x is equal to 2y, and then the curve on the left is x is y squared minus 15. Be sure to subtract that entire thing if it has more than one term. Notice I put parentheses there to indicate that subtraction built into the integral would apply to that entire function. So here I'd use the fundamental theorem of calculus. This is the antiderivative of that. Here are the bounds, and I get that same answer. Of course I get the same answer. There's only one answer. However you do this is 256/3. So all right, you could do it either way. But in this one problem, I wanted to make sure that even though one way is much easier than the other, that you understand the models that we use to set up and evaluate these areas so well that you can do it either way. Okay. Now, I guess if there were no instructions to specify it, you would decide, think about it from both perspectives, and choose whichever way is easiest or most agreeable to you.